airplane model that I have chosen is a very popular home-built plane from Van's Aircraft, called RV-14. I have modified the model a bit to make it easier for you to understand. Let's start with the parts of an airplane. The body of the plane is called fuselage. Inside the fuselage, you'll find the cockpit where the pilot sits and controls the plane, and it is enclosed by a transparent fiberglass canopy. The wings are attached to the fuselage along with fairings on the root, as well as the tip of the wings. The forwardmost section of the plane holds the engine with a propeller, and it is covered by two engine cowlings. In the rear end of the plane, a horizontal stabilizer and a vertical stabilizer is attached to the fuselage. Movable control surfaces like the ailerons and flaps are attached to the wings. Elevators are attached to the horizontal stabilizer, and the rudder is attached to the vertical stabilizer. This entire rear section is called the empennage section. This aircraft has 3 fixed landing gears where the wheels are covered by wheel fairings or wheel pants for aerodynamic purposes. The entire aircraft is covered with thin aluminum sheets from the outside as well as from the inside, and is called the skin of the aircraft. These are the basic parts of an airplane. Let's see how they are built. The fuselage is made of multiple supporting structures called bulkheads and formers, and they are held together with the help of long rod-like structures known as longerons and short strip-like structures called stringers. These kind of small home-built airplanes are made of strong and lightweight materials such as wood, composite materials and aluminum alloys. They are painted with corrosion-resistant paint, which gives them the distinctive green color. The forwardmost bulkhead, to which the engine is fixed, is called a firewall. It is made of fire-resistant material like stainless steel to protect the occupants in the cockpit in case of a fire breakout in the engine section. The outer and inner aluminum skins are fastened to the airframe permanently by riveting. The engine cowlings are made of composite materials due to its high strength, light weight and corrosion-resistant properties. The canopy is made of transparent fiberglass and it provides a greater field of view to the pilot. The entire skeletal structure of the plane is called an airframe. Let's take a look at the wings. 2 strong horizontal beams, called wing spars, are attached to the fuselage. Their main purpose is to carry flight loads and the weight of the wings on ground. Now comes one of the most important part of the wings as well as the entire aircraft, the ribs. Multiple ribs are permanently attached to the spars by riveting. These ribs are designed in a unique shape called airfoil. This shape creates an aerodynamic force called lift, which helps the airplane to fly and stay in the air. We'll study about it in a moment. The stringers provide additional strength and support to the ribs and the entire wing. Behind the ribs, the control surfaces such as the flaps and ailerons are attached to the spar, and both the surfaces are movable. The wings are covered with fairings near the wing roots and the wing tips to reduce drag, and they are made of strong and lightweight fiberglass material. The wings not only generate lift, they also carry fuel for propulsion. Some planes have fuel tank in their wings, but in some planes, there is no fuel tank. The fuel is stored directly inside the wings. These types of wings are called wet wings. They have to be perfectly sealed from the inside to prevent fuel leaks. Along with the fuel, they also carry few mechanisms which are used to move the control surfaces. Let's see how the wings generate lift. There are 4 forces acting on an airplane. Those are the lift, weight, thrust, and drag. Lift is a force that holds the airplane in the air, and most of the lift is generated by the wings. Weight is the force with which the gravity attracts a body, in this case, the airplane. Thrust is a force that moves the aircraft through the air. The airplane's engine provides the necessary thrust. And the drag is a force that opposes the motion of the airplane in the air. It is an aerodynamic resistance and it has to be avoided as much as possible. The main aim of an aeronautical engineer is to design and build an aircraft while aiming to maximize lift and thrust, and minimizing weight and drag as much as possible. If you look at an airplane's wing from the side, it looks like this. This unique shape is called an airfoil. The front end is called the leading edge, and the rear end is called the trailing edge. If you observe carefully, the top surface of the airfoil is curved, and the bottom surface is a bit flat. This curve is called upper camber, and this kind of airfoil is called cambered airfoil or asymmetric airfoil. Another type of airfoil called symmetric airfoil is also used, where the top and the bottom surface of the airfoil has the same curvature. These are the 2 main types of airfoils, and based on these 2 types, hundreds of airfoils have been designed and used. They have to be chosen carefully depending on the altitude, speed and performance you're expecting from the aircraft you're trying to design. To generate lift, there must be airflow over the wings, and to do that, the airplane has to move forward. The engine produces the necessary thrust and pushes the airplane forward. Once the airplane reaches a certain speed, the airflow over the wing increases. Due to the camber on the upper surface of the wing, the airflow on top of the wing is moving faster than the airflow at the bottom of the wing. This means that the air molecules on top of the wing are far away from each other, whereas the air molecules at the bottom are closer to each other. In other words, the pressure on top of the wing is lower than the pressure at the bottom of the wing. This difference in pressure creates an upward force on the wing, and that force is called lift. This is the famous Bernoulli's principle. Also, the airflow on the top surface of the wing is being deflected downwards near the trailing edge of the wing. According to Newton's third law of motion, for every action, there's equal and opposite reaction. This basically means that the downward flowing air is also pushing the wing upwards. All these forces contribute in pushing the wing upwards, which is nothing but lift. Here, both Bernoulli's principle and Newton's laws are in action. This is an oversimplified explanation of the generation of lift. In reality, it's a complex process. We can increase and decrease the amount of lift generated by the airfoil by increasing or decreasing the upper camber of the airfoil. We can do that by moving the control surfaces that are attached behind the wings and the stabilizers. The lift can be increased by deflecting the control surface downwards. This increases the upper camber of the airfoil. Now the speed of the airflow over the upper surface increases, causing the pressure to further decrease. The pressure difference between the top and bottom surface of the airfoil increases, which increases the lift. Also, the air is now being deflected at a steeper angle near the trailing edge, which also pushes the wing up. Similarly, we can decrease the lift by moving the control surface up. The airflow over the upper surface has now been disrupted. This creates turbulence and decreases the lift on the airfoil. By increasing and decreasing the lift over the wings and the stabilizers, we'll be able to turn the airplane in any direction we want. An imaginary straight line passing through the middle of the airfoil is called a chord line. The angle between the chord line and the incoming airflow is called angle of attack. When the airplane is flying straight and level as shown, the angle of attack is 0. The cambered airfoil or the asymmetric airfoil can produce lift at 0 angle of attack, because the difference in curvature between the upper and lower surface of the wing is enough to create the pressure difference required to generate lift. Whereas the symmetric airfoils cannot produce lift at 0-degree angle of attack, because both the upper and lower surface of the wing has the same curvature, and therefore produces the same amount of pressure. They simply fail to create pressure difference at 0 angle of attack. They'll produce lift only when the plane is flying at an angle of attack above 0 degrees. This is the main difference between symmetric and asymmetric airfoils, and this is exactly why the symmetric airfoils are used in places like the horizontal and vertical stabilizers, where lift is not required during most of the flight. Just like the wings, the horizontal stabilizer also has spars and ribs. But the difference is that the ribs used here have symmetric airfoil pattern. This is to avoid unnecessary pitching motion. We'll study about these motions in a moment. Similarly, the vertical stabilizer is also made of ribs with symmetric airfoil pattern to avoid unnecessary yawing motion. Let's see how it works. An airplane has 3 basic movements. They are pitch, roll, and yaw. When the plane's nose goes up and down, it's called pitching. When the entire plane tilts to one side, it's called rolling. When the plane's nose turns sideways, it's called yawing. Primary control surfaces such as the ailerons, elevators, and the rudder are used to turn the airplane in the desired direction, whereas the secondary control surfaces such as the flaps, slats, trim tabs, and spoilers are used to improve the control and performance of the airplane. Let's see how they work. Inside the cockpit, there is a control stick. The pilot moves the stick to move the elevators and the ailerons to pitch and roll the airplane. Elevators are used to achieve pitching motion. Pulling the stick back moves the elevator up. Pushing the stick forward moves the elevator down. The stick is connected to a simple reverse motion linkage. Here the control rods are connected to a link that rotates about a fixed hinge. When the stick is pulled back, the control rods push the elevator up. When the airplane is moving on the runway at high speeds, the wings will generate lift. But this is not enough for the plane to reach higher altitudes. We need to tilt the nose of the plane up to help reach higher altitudes. Therefore, the pilot pulls the stick back and the elevator goes up. The airflow on the top surface of the horizontal stabilizer is now disrupted, which reduces the lift on the horizontal stabilizer. The horizontal stabilizer loses lift and the entire tail section goes down, lifting the plane's nose up. Now the plane can ascend to higher altitudes. Similarly, when the pilot pushes the stick forward, the elevator goes down. This increases the camber on the upper surface of the stabilizer and increases the lift. The tail section lifts up, causing the nose to go down. Now the plane descends. This is how pitching is achieved. Let's look at rolling. Ailerons are used to achieve rolling. They are located at the tip of the wings. They are arranged in such a way that when one aileron goes up, the other one goes down, and vice versa. When the stick is moved to the left aileron goes up, and the right aileron goes down. This is because the control rods are pulling the left aileron up, while pushing the right aileron down. A simple bell crank mechanism is used to achieve this motion. This mechanism helps to turn the control rod's motion by 90 degrees. The left aileron goes up, and decreases the lift on the tip of the left wing, whereas the right aileron goes down and increases the lift on the tip of the right wing. This imbalance in lift creates the rolling motion, and causes the airplane to roll to the left. Similarly, to roll to the right, the pilot moves the stick to the right, which lowers the left aileron and raises the right aileron. Now the lift on the right wing decreases, and on the left wing increases, making the airplane roll to the right. We achieved rolling motion by varying the lift on the tip of the wings. Let's look at yawing motion. Two pedals known as the rudder pedals are located near the pilot's feet. The pilot pushes these pedals to move the rudder to achieve yawing motion. The pedals are connected to the rudder by two strong cables made of galvanized steel. When the pilot pushes the left pedal, the cable pulls the rudder to the left. Similarly, pressing the right pedal will turn the rudder to the right. To achieve left yaw, the pilot pushes the left pedal, and the rudder turns left. This increases the camber on the right side of the vertical stabilizer, and therefore increases the lift on the right side of the vertical stabilizer. This will turn the tail section to the right, and the nose of the plane turns to the left. This is called left yaw. Here, we are creating lift sideways. Similarly, to achieve right yaw, the pilot pushes the right pedal. The rudder turns to the right and increases the lift on the left side of the vertical stabilizer, creating right yaw. By changing the camber on the airfoil section, we changed the lift distribution and successfully achieved pitching, rolling, and yawing motion with the help of primary control surfaces like the ailerons, elevators, and the rudder. Let's look at one of the secondary control surfaces, the flaps. The flaps are located right next to the fuselage. Unlike the primary control surfaces, the flaps only move downwards. Their main aim is to increase lift during takeoff and landing by increasing the camber on the wings. On the left-hand side of the pilot, there is a flap lever. The pilot pulls the lever up to lower the flaps. There is an angle indicator in the lever that shows what degrees the flaps are lowered at. Flaps are usually lowered between 25 to 40 degrees. When the pilot pulls the lever up, the flaps goes down and increases the camber on the wings. This increases the lift on the wings, helping the pilot to control the aircraft during takeoffs and landings. Let's look at the landing gears. This plane has 3 landing gears in a tricycle configuration. The wheels are covered by wheel fairings, or wheel pants, to decrease drag. These gears are fixed gears, they cannot be retracted inside the fuselage. The main gears are attached to the wing spar. They are made of strong composite materials, and are made a bit flexible to absorb shock during hard landings. The nose gear is attached to the engine mount, and it has a shock absorber. It can turn to steer the airplane on the ground. In other airplanes, the nose gear is connected to the rudder pedals and they can be controlled directly. But in this plane, the nose gear rotates freely like a shopping cart wheel, and it has to be controlled indirectly with the help of differential braking. Let's see how the brakes work. Both the main gears have hydraulic brakes which are controlled by the brake pedals. The brake pedals are attached to the rudder pedals. These pedals can rotate and are used to apply the brakes to stop the plane on the ground. Hydraulic brake cylinders with a piston are fixed right next to the brake pedals. When the pedals are pressed, they rotate and push the piston inside the cylinder. The brake fluid in the reservoir goes through the pipes and reaches the brake calipers. Now the brake is applied and the wheel slows down. The brakes can be applied individually. When the brake is applied on one wheel while the other wheel is spinning, it's called differential braking. To steer the nose wheel to the right, the pilot applies the brake on the right wheel. The spinning left wheel will force the nose wheel to turn to the right. Similarly, to steer to the left, the pilot applies the left brake. The spinning right wheel forces the nose wheel to turn to the left. This is called differential braking, and this is how the nose wheel steering is achieved in this aircraft. Colored lights known as navigation lights can be found at the tip of the wings. And on top of the vertical stabilizer, you can find a beacon light. The light on the right wing is of green color. The left wing light is of red color. And the beacon light is of white color. These lights do not blink. They are steady throughout the flight. This is done to identify in which direction the plane is flying at night. For example, if you see the red light to the left and the green light to the right, then the aircraft is flying away from you. Another set of white-colored lights called strobe lights are designed to blink and are used to make the plane more visible to other planes at night. Let's look at the propulsion section. This aircraft uses a Lycoming IO390 4-cylinder internal combustion engine. But the engine you are looking at is the UL520IS engine. This is a 5.2-liter, 6-cylinder internal combustion engine. It weighs around 238 pounds and produces horsepower of 200 HP and 465 Newton-meters of torque. It rotates at 2,800 revolutions per minute in clockwise direction from the pilot's view. It uses minimum 95-octane MO gas fuel, which is stored in the wings. The engine is mounted on the engine mount. The mount is usually made of steel or aluminum and it's attached to the firewall. 2 propeller blades are attached to the propeller hub. These blades are also made of airfoil shapes, placed in different orientations for increased thrust and reduced drag. They are usually made of stainless steel alloys, aluminum alloys, and composite materials. These are puller-type propellers, meaning they pull the aircraft forward. There are planes with pusher-type propellers too. They are usually placed at the back of the plane, and they push the plane forward. This propeller is a fixed-pitch propeller. There are variable pitch propellers too, where the pilot will be able to change the angle of attack of the blades by rotating them, depending on the altitude at which the plane is flying. By doing this, the efficiency of the propeller and the engine is improved. The exhaust gases from the engine goes out through the exhaust pipe, which is located behind the engine. The engine with the propeller provides the necessary thrust to push the aircraft forward in order to create more airflow over the wings and to keep the airplane in the air. In this video, we focused only on the lift. In the future, we'll learn about other important topics such as drag and different types of drags, weight, types of aircraft engines, and types of secondary control surfaces. You now know how an airplane flies. Thank you for watching.